In this work, submitted to IFAC2020, we present the shape and motion planning techniques developed for the reconfigurable aerial robotic chain. We propose a planning methodology for the reconfigurable aerial robotic system of systems named the aerial robotic chain, or the ARC. The ARC consists of multiple micro-aerial vehicles, or ARC units, connected through rigid links and 3 degree of freedom joints with the ability to integrate encoders within them. The motivation of this design relates to the desired ability of the robot to traverse narrow environments while simultaneously being able to carry a significant payload, or cooperatively exploit the thrust vectoring of every ARC unit towards aerial manipulation. Additionally, this design offers the potential for distributed sensing and processing, decentralized estimation and control, as well as enabling system redundancy. One application that we imagine is using the robot as a flying snake to navigate narrow environments to locate disaster victims. Another application is for the robot to carry the wide range of sensors needed for industrial inspection in narrow areas, such as thermal vision, cameras, and LiDAR, while maintaining a narrow cross-section. We propose a novel planning methodology, the ARC Planner, that enables the aerial robotic chain to plan its motion online across narrow environments, making full use of its reconfigurable nature in a fast, collision-free manner. Several contributions in the field of reconfigurable aerial robots have aimed to allow the robots to adapt their configurations based on the assigned task. Dragon demonstrates in-air aerial transformation. It consists of 2 degree of freedom gimbal modules to stabilize the robot and 2 degree of freedom joint modules with motors to change the shape. Dragon uses differential kinematics to plan the motion of the robot to guide it through narrow openings. However, the assumption that obstacles can be represented as primitive geometries may not hold in general. Doddelin et al. Uses a high-level planner to determine which of its defined configurations is best for the current task or environment, combined with a local configuration planner. Our approach is different from this work in 2 main aspects. First, we focus on cluttered environments. Hence, if the configuration library fails to find a solution, we utilize the solutions of a local PRM-based configuration planner to find a valid shape. Second, we replan the translation path when the local PRM planner does not find a solution. In this work, we assume that the offsets between the joints and the robot's centers of gravity are negligible, and in normal operating conditions, every ARC unit's tilt angles are small. The configuration space for the motion planning task includes the 3D position and yaw angle of the first ARC unit, as well as the pitch and yaw Euler angles for each inter-ARC unit link. Denoting n as the number of ARC units, the dimension of the configuration space is 2n plus 2. To control the shape and 3D position of the ARC system, in this work we use one MPC position controller for the position dynamics of the first ARC unit in parallel with n-1 SO3 angular controllers for the angular dynamics of each inter-ARC unit link. From the output of the position controller and the n-1 angular controllers, we can calculate the desired thrust vector for each ARC unit, which is tracked by a fast, low-level attitude control loop within each unit. The proposed ARC planner integrates an arbitrary number of ARC units and employs a 2-step process to navigate the robot from the current position to the goal. We decouple the entire configuration space into separate spaces for translation and shape configurations. The translation planner plans the path for the first ARC unit. For each path segment of the translation planning solution, the configuration planner determines the attainable shape that allows the robot to safely pass over the path segment. The proposed planner uses Octomap as the mapping framework. The translation planner identifies the shortest collision-free paths to the target position for the leading robot by building a probabilistic roadmap. This path is then used by the configuration planner to determine the shape of the robot that would enable collision-free motion. Before moving on to the detailed presentation of the configuration planner, we will define a few terms. We define valid configurations as those that do not collide with the environment at a given position of the leading arc unit. Similarly, we define admissible configurations as those shapes which remain collision-free during the translation of the robot over the given path segment. The set of admissible configurations is a subset of valid configurations. The configuration planner finds collision-free shapes of the robot that allow it to traverse the path selected by the translation planner. We prioritize the known library shape configurations, or LSC, and select the one that requires the minimum cost to transition. If no LSC configuration is admissible, then the configuration planner attempts to find a solution from the pre-sampled set of random shapes, or SRS. A graph is created with valid and admissible shapes in the SRS, and lazy evaluation is performed on the graph to find a solution with the minimum cost to transition. We choose the cost to transition between two configurations as the sum of squares of the difference between yaw angles of the leading arc unit and the difference between pitch and yaw angles of each inter-arc unit link. We use higher weights for the links closer to the leading arc unit to reduce the changes in the angles of these links, which can lead to large motion of the tail arc units. The LSC consists of carefully chosen solutions optimized for particularly challenging environment sections, like narrow passageways, corners, as well as those which maximize the field of view of the sensors. For the arc system consisting of n arc units, the LSC contains the following configurations: a straight line configuration and 3 serpentine configurations, of which 2 are mirrored on the XY plane and 1 configuration lines on the XZ plane, minimizing the robot cross-section. The circular arc shaped configurations are optimized for passing through corners, and the polygon shaped configuration maximizes the field of view of the onboard sensors. The LSC is frequently used in the mission to find admissible shapes quickly. The LSC configurations are prioritized as they often provide admissible, collision-free solutions quickly in trivial environments, significantly reducing the computation cost of planning. Once an admissible configuration from the LSC is found, the planner checks if the transition from the present configuration to the desired configuration is collision-free. The planner then adds the shape transition in the translation to the full state plan path. However, the LSC configurations often fail to provide solutions for narrow, constricted environments where turning is required. We make use of the set of random shapes to provide solutions for path segments in such environments. The set of random shapes, or the SRS, is a pre-sampled set of configurations. A PRM-based method for shape configuration sampling provides admissible solutions for the path sampled by the translation planner and is only utilized when no LSC-based solution is feasible. The shape of the robot is obtained by sampling the joint angles of the connecting links between arc units and the yaw angle of the first arc unit from a uniform distribution. This shape is added to the SRS. The specific environment map is not considered when building the SRS. This step is executed a priori, and as a result, the robot has a large number of pre-sampled SRS configurations at its disposal when needed. In the running phase, a shape PRM is generated from valid and admissible shapes in the SRS when the library of configurations cannot find an admissible solution. The shortest path to the admissible configuration is found using Dijkstra's algorithm, and collision checking is done in a lazy manner. The colliding edges are pruned and the transition path is recalculated. This process is repeated until a collision-free shape transition is found. The planner adds the shape transition to the planned trajectory. Then the configuration planner plans for the shape for the next path segment, and the process continues. Both the solutions of the translation planner and the configuration planner are used to compute the system's trajectory in configuration space, which the controller executes. In cases where the configuration planner is unable to provide a solution for the path segment, the path segment is pruned from the translation planning graph. The translation planner is re-invoked to find an alternate path to the target from the robot's current position. To comprehensively evaluate our approach, simulations were performed using the gazebo-based Rotor S simulator. We present our results in two room-like environments and an application-driven case where the robot plans a path inside a connected silo structure. We compare the performance of the ARC planner when only the LSC or only the SRS configurations or both are included. We also compare our approach with the full state lazy PRM and report the results. In this test, the robot has to take a turn and navigate through an oblique window. In this study, the robot has to navigate to the end of a maze-like room. The environment consists of many narrow L-shaped turns. As a result, the configuration planning stage has to make use of the SRS configurations, and complex shape transitions can be seen. This simulation demonstrates an application of the ARC for inspecting constrained environments. In the first silo, the robot attempts to maximize the sensor coverage using the LSC polygon configuration, following which the planner plans the motion to the second silo using the straight line configuration to minimize the robot's cross-section. The robot again transforms its shape to maximize the sensor coverage. The results of environment 1 are shown in the table. The robot is able to pass through a major section of the environment using LSC configurations. However, it needs to make use of SRS configurations when passing through the window. The results of environment 2 are computed and tabulated as follows. From tests 1 and 2, it is observed that the planning time is lower when both the LSC and the SRS are used, as opposed to either of them individually. We also compare our approach with the full state PRM, where a roadmap is generated in the full configuration space of the robot, and collision checking is performed in a lazy manner. Our approach provides the robot with the ability to utilize a fixed library of configurations and a pre-sampled set of random configurations, hence increasing the speed compared to a full state PRM while still maintaining the flexibility to find admissible solutions in narrow environments. Thank you.